Good morning. Today I would like to discuss steady state approximation and reaction mechanism. Now it is a very simple concept that if you understand the steady state approximation and you know the reaction mechanism, so you can write the rate laws without any problem. Now the question arises that what is actually steady state approximation? Why we call it is a approximation? Because what happens, suppose there is a multi-step reactions and there are some intermediates. So according to steady state approximation, we assume, because it is an assumption, we assume that this transient species or intermediate exist for a very short time and their concentration may be zero. So that is, therefore it is called the steady state approximation method. And in considering that zero condition, we can apply the kinetic equation. And you will be happy to know that this steady state approximation was developed by a very great scientist. His name is Max Bodenstein, because he has actually, you can consider he is one of the founder of the chemical kinetics, and he discovered large number of hydrogen halogen reactions. So for example, H2 plus Cl2 or H2 plus I2 or H2 plus Br2, and you can call it that all the chain reaction, most of the chain reaction was determined by the Bodenstein. And he is a actually German physical chemist. So I will only explain only one simple reactions where there may be more than one intermediates. So as per the steady state approximation, one of the rules is that you have to eliminate all these intermediates. If there is only one intermediate, there is very simple steady state approximation method. If there is a two, then it is little bit different. And in future, I will discuss the hydrogen halogen chain reaction, but today I will concentrate only one simple reaction, that is the bromine catalyzed reaction of the aniline in the presence of nitrous acid. So first I will write that equation, reaction mechanism, and then I will solve steady state approximation as well as the equilibrium method. So let me just explain that simple reactions. The reaction is that C6 H5 NH2. This is aniline, you all know. React with hydrogen ion plus nitrous acid. In the presence of Br, and the product is one of the derivative of benzene, benzene diazonium ion, C6 H5 N2 plus 2H2. This is the total reactions. If you know the reaction, or if you know the reaction mechanism, that means each and every step, then you can write this rate. And the rate is equal to K dash HNO2 hydrogen ion and you can call it the rate law. Now surprisingly, the main reactant is not involved in the rate law. Now what is our question? That proposed a mechanism, consistent with the rate law. That is the problem. Now that problem can be solved by these, as I told you, steady state approximation method. Steady state approximation method. And as well as another method is also there, that is the equilibrium method. Now the first condition of applying the steady state method or equilibrium method, you have to write the most probable mechanism, and on the basis of this most probable mechanism you can derive the rate laws. So let me write the most probable mechanism. I have taken this example from the book of physical chemistry by Ira and Levine. So let me first write the most probable mechanism of these reactions. So mechanism. First step is HNO2 react with hydrogen ion, that is this is actually nitrous acid. It is a rapid step, pre-equilibrium step. H2NO2 plus. Fast step, fast, you can call it a fast. And K1 is K1, K inverse 1. Now the second step, H2NO2 plus react with that bromine catalyst till form NOBr plus, I think, H2. And similarly the rate constant is K2. And third step is of course C6 H5 NH2 plus this NOBr, and finally we'll get C6 H5 plus H2, and I think this. Okay, and this is K3. And definitely this is a first step, so it is also slow step, and this is also slow step. Now what is the importance of this reaction? Because here there are more than one intermediate. Because if I write the total or overall reactions, you will find that I will write that because this part is the intermediate part, this part is also intermediate part, and this is also intermediate part, this is also intermediate part. So it will only the things is HNO2, H and aniline in the presence of bromide ion, that is product will be formed. So now how steady state approximation is applied for that reaction? That is the objective of today's lecture. Now very simple is that the first step of any steady state approximation is that identify the slow step. Now in kinetics there is a terminology, sometimes it is called the mathematical simplicity or matter of convenience, because there are two steps. Maybe step number 3 is very slow, or sometimes step number 2 is also slow, but the matter of convenience is that how do you determine this rate? Now if I want to monitor the step number 2 and it is rate determining step, yes, it is also slow step and you can consider the rate determining step, but the problem is there that here NOBr is produced, but in the next case NOBr is consumed. But if I consider the step number 3 where the final product is formed, and if I monitor the concentration of the product, I can determine the rate. So as a matter of convenience, the step number 3 should be the rate determining step. So therefore I can write rate is equal to third step. So it is K3 C6 H5 NH2 and why I have written the red color? Because it is intermediate, NOBr. So now the role of steady state approximation means I have to eliminate NOBr, and as per the steady state approximation, the concentration of the NOBr must be 0 or constant. So what I have to do? I have to substitute the value of NOBr from that mechanism to this equation. So I can write d by dt of NOBr is equal to. Now from that mechanism, in here NOBr is produced, and step number 3, NOBr is consumed. So because NOBr is produced, so I can write like that K2 H2 NO2 plus and Br. Now why minus? Because in step number 3, the concentration of NOBr is decreasing. So I should write K3 C6 H5 NH2 and NOBr. Now the role of steady state approximation. According to steady state approximation, the concentration of this, that means I can write like that, d by dt of NOBr is equal to 0. So I can write here 0. That is equal to 0. That means, so this is K2 H2NO2 plus Br negative. If it is 0, so I can write like that K3 C6 H5 NH2 and NOBr. I have to determine the NOBr. So NOBr is equal to K2 H2 NO2 plus and Br divided by K3 C6 H5 NH2. So that means applying steady state approximation, we are able to determine the value of NOBr. Now we have to substitute this NOBr to here and our problem will be solved. So how do you solve this equation? So just you substitute the value of NOBr from here, so here. So finally the rate is equal to K3 C6 H5 NH2, and in place of NOBr we can write H2 NO2 plus Br negative. K2 is also there, so I can write also K2, I can write here also, no problem, divided by K3 C6 H5 NH2. So this can be cancelled out. So even this also cancel out. So finally we will get K2 H2 NO2 and Br. So you must be happy that our problem is solved. But no, now the last step we have to solve, because here again this is also an intermediate. So in the last step, this H2NO2 must be eliminated, again applying the steady state approximation method. That means we have to eliminate this H2NO2 and you will get the final rate law. It is a very simple example of steady state approximation. There are so many examples available in the various books of the physical chemistry, N2O5, decomposition of N2O5. There are so many examples, but I am taking a example where there are two intermediates. So last step is that the elimination of this H2NO2. So let me erase this part also. So the last step, I can also eliminate all this part. Because there is only one step is there. So I should again write, so rate is equal to, where I am getting K2 why I have red color, because it is the intermediate H2NO2 plus and Br. I should not write this because this is not intermediate. So I have to eliminate H2NO2 plus and you will get the final results. So from where I get this H2NO2, the first step. In one case, H2NO2 is produced. In another case, H2NO2 is consumed. And in third step also H2NO2 is consumed. So I can write like that, d by dt of H2NO2 plus is equal to, because this is the intermediate. First it is produced, so I can write K1 HNO2 and H. Because it is produced, therefore it is positive. In reverse case, it is consumed. So K inverse 1 H2NO2 plus. And again in third step or second step, it is again consumed. So it must be minus K2 H2NO2 So there are very simple step, that last step, that again we apply the steady state approximation method, d by dc is equal to 0. So you can write like that, we can write like that, K1 HNO2, and simply solve it. There are two ways. You see, very simple. If left hand side this part is 0, so we can write K1 HNO2, this is equal to, because this HNO2 is common. So I can write, if I write like that, H2NO2 plus common, you can write like that. So K, this is I think K inverse 1. K inverse 1 plus K2Br negative. So H2NO2 you can directly write. So I should write H2NO2 NO2 plus intermediate. Or if you understand, you can directly write, because this part can be eliminated. You can apply in the denominator part. So this is equal to K1 HNO2 H divided by denominator part K inverse 1 plus K2 Br negative. So the last step is that we can substitute this value of HNO2 from here to our last equation. You will get the rate loss. So last step, rate is equal to so K2 in place of HNO2 we can write, or you can write other part also, K1 HNO2 then H then Br negative divided by K inverse 1 plus K2 Br negative. This is the final rate loss where that main reactant is not involved. So it is, you can write like that. You can write with a constant. So HNO2, H and Br. And then again, what about this denominator values K inverse 1 and K2 Br? It depends. When you perform a complete experiment, suppose this K1 step, if you compare with that K, because both these steps are very slow steps. Suppose the value of magnitude of the K inverse 1 is very low, you can remove this part. So that will only, this part will be there. Or suppose this step number 3, the magnitude of the K2Br is very low, suppose. Because basically, as I told you, that there are two slow steps. So in some cases, it is slow, so you can remove it. And so you can write that K2, K1, K1 is the constant HNO2 which is consistent with the mechanism. So this is the one of the simplest example of the steady state approximation method, and there are a large number of examples available in the various books of physical chemistry like Irayan Levine, Atkins, Alberti and Daniels. There are so many examples are available, and the best thing is for the student is that you should write some of the simple example and then apply steady state approximation method. So how do you know that your system is correct? Because when you apply this steady state approximation method, this is the mechanism and this is the rate law. Suppose you are getting the rate law which is consistent with that mechanism, then you can say yes, your mechanism is most probable velocity, most probable mechanism, and it is correct. So this is the simplest example of steady state approximation method. In my next lecture, I will discuss some of the very important chain reactions. H2 plus Cl2 is equal to twice HCl, or H2 plus Br2, H2Br, H2 plus I2, and why the rate laws are different for all these three hydrogen halogen reaction. And of course, with the help of steady state approximation method, we can figure out the rate laws of all these very important chain reactions. Thank you very much.